Hello and welcome to our third lesson in Unit 4. Today's lesson is going to be on half-life. As we continue our lessons talking about the nucleus of atoms, today we're going to focus on some specific types of radioisotopes, and we're going to take a look at what their uses are. And then at the end of the lesson you should be able to calculate the initial amount, fraction remaining, or the half-life of a radioactive isotope when you're given two of those three variables. And you can see kind of from this initial picture here a little bit of what half-life might mean as we go from an original sample here to one half-life later of that same sample. You can kind of see a different color there indicating that we had some type of change. And we're going to take a look at what that change means in a moment. First, I want to talk to you about uses of a few different common radioactive isotopes. You can find these in a little bit more detail on page 13 of your Unit 4 notes. The first one I want to focus on is iodine-131. Remember, I-131 is isotopic notation. That's referring to the isotope iodine-131, which would contain 131 protons and neutrons. And this particular radioisotope is used in diagnosing and treating thyroid disorders. Now the key for this, anytime you see thyroid, you want to try and think iodine. And these tend to show up on the regions fairly often. The next type is carbon-14. Now carbon-14 along with iodine is not below our atomic number 83, which is our cutoff line for naturally occurring non-radioactive elements. But that means carbon does have a stable isotope, carbon-12, but it does have others that are radioactive, and one of these is carbon-14. And if we compare the ratio of carbon-14 atoms to carbon-12 atoms in a particular sample, we can use that ratio to determine how old a once living organism is. So when you see the carbon-14 isotope, we want to think that it's used to date once living organisms or living things. So we see carbon, we want to think living things. Similar to the carbon-14 carbon-12 ratio is the uranium-238 ratio to the lead-206 ratio, and that's going to be used in a similar manner to date geological formations. So when we see uranium-238, we want to think geological formations, rocks, or the earth itself, and how old that could possibly be. And these ratios that we're talking about, uranium to lead or carbon-14 to carbon-12, these are going to help us determine how old a particular sample is, because we know through experimentation how long it takes for these radioactive isotopes to break down. And we'll get to that in more detail in a moment. The last one you need to be familiar with is cobalt-60. It's our last radioactive isotope that you need to be aware of our four common ones here, and it is used to treat different types of cancer. And again, you can take a look at page 13 if you would like to review those in more detail. Now what we're going to focus on with today is half-life, and what half-life means in regards to radioactive isotopes. Now radioactive isotopes undergo radioactive decay, and this particular process is random. We can't quite predict it with any certainty, how much, when it's going to happen, but we can make a fairly accurate prediction about how many particular nuclei in a large sample are going to decay in a certain amount of time. And this is going to change depending on the element that we have. And we know that radioactive isotopes are radioactive because they're not stable. They don't have a favorable proton to neutron ratio, and therefore try and undergo some type of natural decay, beta, positron, alpha, to try and make their nucleus more stable. And that's kind of the driving force behind why atoms are undergoing these changes to become more stable. Now the half-life is a period of time that must go by in order for half of the nuclei in a sample to decay or to change into something else. Now, during this half-life period, or during one particular half-life period, we know that of all the radioactive nuclei that are in the sample, half of them are going to decay into new, more stable nuclei. And it doesn't mean that it's going to be the same element. Chances are it's going to change what the element is. But it's going to be more stable. And that's the key here. So during one half-life period, regardless of how long it is, we can expect half of that sample to turn into something else. For example, if we started with 10 grams of carbon-14, after one half-life, regardless of how long it is, we would be left with 5 grams of carbon-14. The rest of that would have been changed into something else. During the half-life, half of the mass of the radioactive isotope is converted into a new, more stable isotope. Now, this is kind of a similar concept when we're talking about nuclei and mass, because, well, nuclei have a mass. So we can be talking about specific nuclei or specific atoms, or in general, which is more common, the actual mass of the radioactive isotope that we're dealing with. And one of the tools that we use to measure radiation is a Geiger counter. And these you might see in movies. Sometimes people have them handheld, and they're counting how many of these decay particles are actually entering its detector. So it's counting, depending on the time period selected, how many of these radioactive particles it is encountering. And the higher that is, the more radiation there is. The lower that is, the less radiation that is. But if we were using a Geiger counter to measure half-lives, after one half-life, that Geiger counter is going to be counting half as much as it was before, since half of those radioactive nuclei were changed into more stable nuclei that are no longer radioactive and emitting radioactive particles, like beta particles and positron particles. Now, what we'll really focus on with this today is how to solve different half-life problems. And to do that, we're going to use some information on Table N, where we can find the half-life of many different radioactive isotopes. And these are often, or at least in this table, referred to as nuclides. So, for example, we've been talking about carbon-14. Carbon-14's half-life is one of the larger ones, 5,715 years. So if we're talking about one nuclei of carbon-14, it's going to take roughly 5,715 years for that one nuclei to change into another isotope and become more stable. Gold-198 has a much smaller half-life, 2.695 days. And calcium-37 has an even smaller half-life. So this is much more unstable compared to the carbon-14, considering its half-life is significantly shorter. Meaning calcium-37 can't even exist for 0.2 of a second, or 0.002 of a second, before it's going to change into something else through positron decay. So we're going to use Table N a lot to find half-lives as well as decay modes, and some other information regarding the nuclides and the nuclei itself. So in order to solve these half-life problems, there are a couple different forms that we're going to see. One of the types that you'll see is where you have to determine how much of a radioactive isotope is going to be left after a certain amount of time. And we might know how much that we are going to start with. And then we'll see a couple different types. We'll start with this one first. Now, the first step to solving one of these types of problems is to determine how many half-lives have gone by. And I'll point out here there's a couple different pieces of information that we want to make sure we have for each one of these types of problems, and we'll do an example of each type. So we want to determine how many half-lives have gone by. Now, in order to do this, we take how much time has gone by and divide it by the duration of the half-life. And I'll break that down a little bit more on the next slide. But this part is important. We take the elapsed time, how much time has gone by, and divide it by the duration of the half-life. That'll tell us how many half-lives that particular radioisotope has gone through. We then have to cut the amount, whether that's a mass, a percent, a fraction, number of nuclei, those are the 4 types you'll see, in half as many times as there are half-lives. And that's really the extent of these problems. For example, the half-life of Rn-222 is 3.8 days. If today the basement or your basement contains 20 grams of radon-222, how much will remain after 19 days, assuming no more leaks in and what we started with is all that we have, which if you have radon in your basement is probably not the case. So we already know the half-life of radon-222. It's 3.8 days. We know the starting amount that we have. We're going to start with 20 grams of radon-222. And we want to figure out how much is going to remain after 19 days. So to figure out how many half-lives that radon-222 is going to go through, we're going to take the elapsed time. I'll abbreviate that ET, or time elapsed. And we're going to divide it by the half-life time, or HL. And that's our half-life time. So we're going to get 19 days over 3.8 days, which is our half-life. And during these 19 days, that radon-222 is going to undergo 5 half-lives. So in order to figure this out, how much is remaining of that 20 grams after 19 days, we know that the 20 grams is going to undergo 5 half-lives. So we cut that starting amount, 20 grams, in half 5 times. And I like to put this right over the arrows because it helps keep me this organized in my head. This is 2 half-lives, 3 half-lives, 4 half-lives, and 5 half-lives. And I always put that over the arrow, which is separating one amount from the other, indicating that a half-life has to go by in order to cut the amount in half. So we started with 20 grams, and after 1 half-life, that 20 grams gets cut in half to 10 grams. After the second half-life, it gets cut to 5 grams, and we're just cutting this in half each time. After the third half-life, it gets cut down to 2.5 grams. After 4, down to 1.25. And after the fifth, we're down to just over 0.6 of a gram left of that 20 grams of radon-222. This is the amount, 0.625 grams, that's still in your basement. The other, let's see, that would be 19.375 grams would be some other more stable isotope, but it's likely not going to be the radon-222. And in the process, this is why radon in the basement is a concern. In the process of this radon decaying into a more stable isotope, it's shooting off these particles that are traveling at the speed of light, beta particles, positron, alpha particles, that can cause problems. That's radiation that can cause problems with biological tissue. So radon in the basement is something that you would like to get remediated as quickly as possible. So we'll do a couple different examples here so you can see how each of these different types are done. For the first one, what is the length of time required for K42 to undergo 3 half-lives? Now this is one we can actually find the half-life for on table N. And K42's half-life, according to table N, is 12.36 hours. And that's for every 1 half-life. And we want to figure out how much time is required to undergo 3 half-lives. Well, if it's 12.36 hours for every 1 half-life, and we want to undergo 3 half-lives, when we multiply these together, our half-lives cancel. We're left with time. So we get 12.36 times 3, and that gives us a total of 37.08 hours. And we're going to keep that just as is. So K42 will take 37.08 hours to undergo 3 half-lives. So we just multiplied the half-life times the total number of half-lives. And we can see there in the math that our units cancel, leaving us with time, which is desired. For the second one, we have an original sample of a radioisotope that had a mass of 10 grams. So our original mass is 10 grams. After 2 days, 5 grams of the radioisotope remains unchanged. So our elapsed time, or time elapsed, is 2 days. And after that 2 days, we were left with 5 grams. We want to figure out what the half-life of the radioisotope is. Now we know, and I do this pretty similarly with most of these, I like to do a little graphic showing starting and ending amounts. So 10 grams, regardless of the half-life, after one half-life, it's going to go down to 5 grams. If it went down to 2, or went through 2 half-lives, it would go down to 2.5 grams. Well, this is where we want to end. The question says after 2 grams, there's 5 grams, or after 2 days, there's 5 grams left that are unchanged. So to get from 10 grams to 5 grams, this has to undergo 1 half-life. And since we know that the elapsed time to get from 10 grams to 5 grams was 2 days, that's going to be our half-life. Half-life of 2 days. It would then take 4 days to undergo 2 half-lives and get down to 2.5 grams. So after 2 days, we have 5 grams of the original sample and 5 grams of some other unknown, more stable isotope. For the third type, we have a radioactive element that has a half-life of 2 days. We don't know what the element is, but we know that the half-life is 2 days. What fraction of the original sample will remain after 6 days? Now our elapsed time is going to be 6 days. And now if we take from our equation from earlier, if we take our elapsed time of 6 days and put it over the half-life of 2 days, it'll tell us the number of half-lives that these samples are going to go through. So during this elapsed time of six days, this radioactive element is going to undergo 3 half-lives. Now when you see one of these types of problems and it talks about a fraction or a percent and it doesn't give you a specific starting amount, we can assume that the starting amount is going to be 100%, or in the case of a fraction, an equivalent fraction that's 100% would be 1 over 1. So if we start with 1 over 1, or 100%, after 1 half-life, which we know is 2 days, this 1 over 1 fraction gets cut in half to 1/2. So now after 1 half-life, we're left with 1/2 the amount that we originally started with. And we know that we have to do a total of 3 half-lives. So we're going to cut this in half 2 more times. So after our second half-life, 1/2 gets cut in half again to 1/4. And if you want to use decimals, just to kind of keep this straight, I always find it's a little bit easier to work with decimals than it is to work with fractions. After 3 half-lives, we're left with 1/8. So after 3 half-lives, after 6 days, there's 1/8 of the original sample remaining. The other 7/8 have been converted into a new, more stable isotope. Last one here, we have the half-life of a radioactive isotope at 20 minutes. 20.0 minutes. What is the total amount of a 1 gram sample of this isotope remaining after 1 hour? Well, we know we're going to start with 1 gram, but we don't really know how many half-lives this is going through. In order to figure that out, number of half-lives, we want to take the elapsed time, which is 1 hour, and put it over the half-life of 20 minutes. Can this work? No, because we have hours and minutes. This has to get converted. 1 hour gets converted to 60 minutes over 20 minutes. And this comes down to 3 half-lives. Now after 1 hour, we're going to undergo 3 half-lives, so this 1 gram gets cut in half. So after 1 half-life, we're now left with 0.5 grams. After 2 half-lives, we're left with 0.25 grams. And after the 3rd half-life, we're left with 0.125 grams remaining of that radioactive isotope. Now those are the 4 types you're going to see. I would always make sure for each of these types of problems that you draw this graphic showing the amounts and the number of half-lives, so you can kind of keep that straight in your head. Make sure you're identifying in the problem what amounts or quantities you have and identify them over on the side, and make sure you're showing all your work. If you guys have any questions on what you come across here or anything you saw in the video, please come see me and let me know. Have a wonderful day.